Welcome back to differential calculus. So in this video I want to talk about, well, I might call it function composition, but really what we want to do in differential calculus is we want to take a big messy function and decompose it into smaller pieces. So really this is about function decomposition. The idea here is that at this point we know how to differentiate lots of basic functions, powers of x, e to the x, trig functions, stuff like that. And we know what to do when functions are combined in some ways. We know how to do it when two functions are added, when two functions are multiplied, when they're divided, but there's a really important way of combining functions that we don't know how to deal with yet, and that's function composition. And today, or in this video, I just want to talk about composition and decomposition, and then next time in class we'll learn how to do calculus, but you need to understand composition pretty well before you can do calculus with it. So let's just talk about function composition. Let me remind you what it is. So basically we have these two functions. We have f and g, and we put them together by putting one function inside the other one. Okay, so the notation for this is like f of g of x. That means first you start with x, then you do g to it, the g stuff, and then you do f to that result. Okay? So I often think of g of x as the inside function, and then f of x is the outside function. Okay, so the inside function is the thing you do first. If you were going to put it in your calculator one step at a time, first you do g to the number, and then you do f afterwards. Okay, so we always read function composition from the inside out. Alternate notation for this would be f circle g. That's not an O, it's a little circle. It means f compose g, and then you write of x. I don't use that one as much. I prefer the f of g of x with the parentheses. So before we decompose, let's make sure we know how to compose functions. So suppose we have these two functions. Maybe you have, well, I don't know, f of x equals square root x, and g of x equals sine x. How can we compose these? Well, when I write f of g of x, what I think is that I take g of x, the whole thing, sine x, and I stick it inside f. So you don't want to think of f of x as square root of x. You want to think of f, not f of x, but just f as square root. So when I say f of anything, that means the square root of that thing, whether the thing I'm putting in is x or y or 3 or sine x. F takes any input, anything you put inside f, and it spits out the square root of that input. Okay, so when I take f of g of x, that means I do the square root. That's what f does. It does square root of whatever, square root of g of x, which, as we can see, is the square root of sine of x. If I want to do g of f of x, which I can certainly do, at least for some x's, whenever I see g, I want to think that g does the sine of whatever I put inside. So g of f of x is the sine of f of x. Just whatever is inside the parentheses for g, that's what I put in as sine. Okay, so that's going to be sine of root x. And note that these are totally different functions. Okay, if you compose in a different order, you get totally different functions. So if I were to ask you how to differentiate square root of sine of x, until you know the chain rule, you don't really know, right? It's made up of functions we know how to integrate. We know how to integrate square root. We know how to integrate sine. But the composition, we don't know how to, or I just said integrate, differentiate. We know how to differentiate root x and sine x, but we don't know how to do the composition yet, and that's what we're going to get to. Okay? Okay. So another way you might see this, or another way we think about it, is sometimes you think of each kind of a chained together series of variables. And this is more how Leibniz would have thought of composition. So say you have like some number r equals some function of t. We'll say r of t. And that's the radius of a circle at time t. Okay, so t is time, and then maybe you have like an oil slick on water or something, and the radius of the oil slick is growing as time passes. And then, well, we can compute the area. Let's say A of r is the area of a circle. So, well, we know that. Let's say we know formulas for these. So let's say r of t is t squared. So it's growing pretty fast as t gets big. And then we know the area of the circle is going to be pi r squared. And if we compose these, we can find Well, we know the radius is changing with time. The area changes when the radius changes. So as time changes, that changes the radius, and that changes the area. So the area actually depends on time. We can say A of R of t, or we can say A compose R of t. So this is going to tell us how the area changes with time, and all we do is we take pi, and then instead of r, we know that r equals t squared, right? So instead of r, I'm going to write t squared, and then I do the a function to it, so I multiply by pi and I square it. So a of r of t would be pi t to the fourth. And that tells me how the area depends on time. Okay, so that's kind of how we use these in practice. One thing changes another, that other thing changes a third thing, that third thing changes the fourth thing, and so on. Okay, so what we want to be able to do is decompose functions. We start with a big messy function that is a bunch of stuff glued together, and we want to be able to pull it apart. Okay, so we have some function like this, and we want to write it as f of x is like g of h of x. Okay, so we have a messy function, square root of 1 minus sine x. We want to pull it apart into smaller pieces. Now, there is more than one way to do this, right? We could say that g of x is, oh, I don't know, square root of 1 minus x, and then h of x is sine x. So g of f of h of x would be, well, square root of 1 minus is what g does. Right, that's g. And then when I put h in for x, I get 1 minus sine x. So fine. But the problem is I don't know how to differentiate g. So not so good. When I pull these apart, there's usually lots of ways to do it. And I get to pick as long as each piece I know how to find the derivative. So I'd rather do it like this. I'd rather say g of x is the square root of x. H of x is 1 minus sine x. I get the same result. I still have that g of h of x is the original function I started with, square root of, so g does square root now, and the thing I'm putting into g is 1 minus sine x. So I get the same result, but now each of these, root x and 1 minus sine x, I know how to differentiate those. So that's a better decomposition for calculus purposes. Okay? So how do I usually think of it? Normally we don't bother to write out g and h every time, and once you get more comfortable with this, you won't have to. What we want to do is we want to think of it as an inside function and an outside function. So if I see square root of 1 minus sine x, I'm going to think, oh, well, here's the inside. That's 1 minus sine x. Here's the outside. No problem. Okay, I don't really have to write out explicitly, this is g, this is h. I just want to know what the pieces are so that I know how to take the derivatives. Let's try a few more. This one, oh, 1 over 1 plus e to the minus x squared. This you cannot break into two pieces, each of which you can differentiate as basic functions. But that's okay, we can decompose something into more than two pieces. So I'd say the 1 over the squaring is the outside. So that's the outside function. That's what you do last. And then 1 plus something is the middle. And then e to the minus, 1 plus e to the something is the middle. And then negative x is the inside. Okay, so that's a little messy. Let's write it down. Let's say we want to write f of x as g of h of, and then I always run out of letters here, let's say L of x. Yes, there are always lots of parentheses when you do this. So the outside function, g, the last thing I ever do is I square it and flip it upside down. So I'd say g of x is 1 over x squared. That's the outside, that's the last thing I do. The middle function is I take 1 plus e to some power. H of x can be 1 plus e to the x. And then the inside function, if I were putting this into a calculator or doing it by hand, the very first thing I would do with an x is I'd make it negative, right? So I'd say L of x is negative x. So let's just make sure this works. If I do h of L of x, well, h says I do 1 plus e to the L of x, right? H just takes 1 plus e to whatever the input for h is. And L of x is negative x, so this is 1 plus e to the minus x. And then what g does, I'm putting in h of L of x here. So I want to think of h of L of x as the input for g. What g does is it flips it upside down, and then it squares it. So this should be 1 over h of L of x squared, which it is. It's 1 over h of L of x, that's this. So 1 plus e to the minus x squared. And again, there are lots of ways you could break down this function. You can decompose it many ways, but the way I did it with these three pieces, I know the derivative of each piece, and that's really important. Okay, so let's just try a few more. This is one you see all the time and sometimes gives you trouble because we write sine to powers funny, right? So whenever you see this, you should probably think of it as sine x to the 4th power. Then it makes it much more obvious that this is the outside and sine x is the inside. Right? If you have an x, first you take the sine, then you raise it to the 4th power. So I would write this as g of h of x, where the outside is the 4th power function. Notice I didn't say x to the 4th, but it's just the thing that raises things to the 4th power. So g of x is x to the 4th. G of anything is that anything to the 4th. And h of x, well, you take anything, you take the sine of that thing. Okay, and then we can see g of h of x is sine x to the 4th, which we always write like this. You just have to be careful. Okay, and of course I can combine this with other things. Maybe I have a cosine cubed of 2x. Again, I'm going to need more than one function here. So the outside function is the cubing, right? That's the last thing I do. Then the middle thing would be the cosine. And the inside, the very first thing I do, would be multiply by 2. So let's try it. F of x is supposed to be 3 pieces now. G of h of L of x. Lots and lots of parentheses. Oh, did I write too many? 1, 2, yeah. Okay, so what's my outside function? The last thing I do is I cube it. So g is the cubing function. What's h? Well, h is the thing I do in the middle. That's going to be the cosine function. And L, the very first thing I would do would be multiply by 2. And I'll let you check that that works out. Okay, so let's try one more, something like this. So it looks like a big old mess, right? But it's not actually that bad. I can write this as a composition of 2 things I know how to differentiate. I don't have to break it down into a whole bunch of bits. I'm going to treat this whole thing as the inside, the whole quotient. And then I'll just have square root be the outside. So, well, let's say this equals g of h of x. So what's g? G is the outside. What do I do last? I take the square root. So g of x, or let's say g, is the square root function. And then h has to be everything that's inside the square root, right? So this has to be 1 minus sine x over 1 minus cosine x. And you're like, oh, but that's such a complicated function. Why would I break it? Because I know how to differentiate that. That's just quotient rule. So it's okay if this piece is a big mess, because it's a big mess I know how to deal with without decomposing further. Okay, so totally fine. So you should get lots of practice with this. It's really important to be able to break things down in your head, especially when we use the chain rule to differentiate compositions. So make sure you do lots of practice. I'll see you in class.